Everyone, I'm Ilya Maksymets, and today I'm going to talk about the OpenFlow Classifier, which is a topic that wasn't brought up in conferences, I guess, for a long time, but also not even came up a lot in mailing list as well. I'm pretty sure the last major uh, change in the OpenFlow classifier was made in around 2016, about 9 years ago, and that's actually the point of this talk. To probably most of you never looked at the OpenFlow classifier, how it works, what it does, how it achieves what it tries to achieve, and sometimes there are issues that rise, and you need to know how the classifier actually works in order to understand how to overcome them, how to write better OpenFlow pipelines, and in general, be nice to OVS and to get the best of it. And yeah, we had quite a few issues in the past year related to different scalability problems, let's say, with the data path, where OVS suddenly starts to generate a huge number of data path flows, degrading performance. And we had a few fixes for this, both in OVS and OVN. So I'll be referencing those while going through this presentation, as they are like a primary motivator of getting people more familiar with how classifier works, so they can navigate those issues and solve them. So first of all, let's take a quick look at how OpenFlow rules look like in general. Just a quick reminder, if you never see them, if you never saw them, that's strange, but happens. So we have some priorities, some match criteria, some actions to execute. And what's the classifier actually is? Classifier takes your packet and runs it through all the OpenFlow rules in order to find the highest priority rule that matches the headers of the packet. And this is a primary goal of classifier, and has also the secondary goal is unwildcarding, which we'll explore a little bit more next. But first, let's look at if you ever run OF_proto_trace, which is a command that actually runs your packets through whole OpenFlow pipeline and tries to tell you what's happening and show what's the final result. You may have seen this kind of output. Here we are running OF_proto_trace on the previously shown OpenFlow rules for the packet with the destination 192.168.0.7. We get some matches, and we get some megaflow in the end. So every time you see this kind of output in the proto_trace, it means that the packet did match an OpenFlow rule in table 0 with priority 100 with this match and these actions on it. And by the end of the whole processing, classifier in the process of unwildcarding generated the following matches for the packet. So going back to the goal, what's the goal of unwildcarding? We are trying to produce a mask, a wildcard mask that indicates which of the bits of the packet headers were significant to produce the result, to match on specific OpenFlow rules and execute the actions. So one bit in any position of the mask means that this particular bit was significant, and if it changes in the header, then potentially the outcome of running this packet through the OpenFlow pipeline would change. 0 bits mark that those particular bits have no effect on the classifier processing. And unwildcarding, the term that we use internally in OVS, that practically means just turning wildcarded 0 bits into exact match 1 bits. So the properties, wildcard masks have some properties, yeah. Sometimes we can get false 1 bits. So some bits are set even though classifier didn't really need them in order to make a decision. Those are usually acceptable, but not desirable. So you don't want your masks to be very wide. False 0 bits are, on the other hand, are not acceptable. If something was used to make a decision, it has to be in the mask. If it's not, it will cause an issue later, as different packets will match this rule later and perform the wrong actions. 0 bits are desirable in most cases, mostly because smaller mask means the data path can actually match more types of packets using exactly the same rule without sending packets to user space to be processed again. And the one interesting property of classifier as well is that wildcard masks for lookups in a given classifier yield a non-overlapping set of rules. This is a bit tricky thing, but what does it mean is if you get all possible combinations of headers and run them through your OpenFlow classifier, and get all the resulted megaflow masks. Then, if you use those masks in a different classifier with the same priority, you will never have overlapping rules in those masks. So each of the masks that generated by the classifier is unique, and if different headers generate different masks, those masks are mutually exclusive. So let's actually take a look at what the classifier actually doing, how it's designed. Here you can see I'm representing the packet headers this way. It's a basically representation of a struct flow that you can find in the code. We have some metadata first, then layer 2 headers, layer 3, layer 4 headers, and stuff. Yeah, let's make an experiment. Let's say we only matching on L2 source and destination in our OpenFlow rules. And they look somewhat like this. We match on MAC addresses, source and destination, and execute some actions. So those will land into L2 part of the struct flow. And what we do now is we take every rule combination that we have, get those source and destination addresses from every rule, and create a hash table out of them. So when we get a packet to examine, we extract source and destination addresses, we hash them, perform a hash table lookup to find which rule is corresponding to this pair of source and destination addresses. Quite simple, I hope. It's just a one hash table lookup. What we have different types of OpenFlow rules, though, if they're not only matching on source and destination MACs. Let's say we have more rules that match on input ports, which are part of the metadata part. Easy. We do 2 hash maps, one for input ports and one for Ethernet source and destination. We perform both hash lookups. So we hash the input port lookup in its own hash table. We hash the Ethernet source destination, look up them in their own hash table, and get two results. Practically, we now have two rules that we found. What we do next, we just take the one with the highest priority. The one with the highest priority of these two is what we are looking for. The masks can overlap. It doesn't have to be like separate fields in the structure. This doesn't change logic at all. We can just hash this part and look up and hash this part separately and then look it up as well. And again, the result will be the rule with the highest priority from all of these hash tables. So overlapping supported. Non-contiguous masks as well. It doesn't have to be sequential fields. We can just take random bits from the mask, hash them, look up, and so on. We can just pick arbitrary bits from the struct flow, take one bit from the source address, one bit from the transport ports, one bit from metadata. This also works, or we can do all of the above. Just a general mix and match of everything that we can imagine. It's pretty simple design, and it seems to work pretty well. So to recap the workflow on OpenFlow rule insertion, we will need to find all the unique match patterns. And then we'll need to create a hash table for each of these unique match patterns, which are called subtables in OVS. Then we put all the rules in their respective subtables. And on lookup, we go over all the subtables, calculate hashes using bits from the mask of this particular subtable, perform a hash table lookup, and out of all the rules found in all the different subtables, we just pick the one with the highest priority. And that's our result. There are some optimizations possible, like we can track, well, OVS tracks what's the highest priority rule in a particular subtable. And in this case, if we found a rule in one subtable, we know its priority, then we can just skip all the subtables that have only rules with lower priority, as they cannot contribute to the final result. So lookup complexity is pretty simple. It's odd 1 for the hash map lookup, but it's odd n for the subtable traversal. Like going over all the subtables and looking up our hashes in each of them. And it's a worst case if the worst case is, as usual, the packet that doesn't match anything. The packet that doesn't match anything has to go through all subtables. And the n in this composition is the number of unique masks that you have in the same table. So it's a potential performance concern, since there are a lot of bits in the struct flow, and there are lots of combinations of those bits. So potential sources of this problem, users, of course, because they are the ones creating OpenFlow rules. So watch out. And another one is maybe one interesting one is OVM creating a lot of different OpenFlow rules with single or a few bit masks while translating inequality matches. For example, if in Kubernetes world, in OVM Kubernetes, it will be like a network policy with an accept block that can generate a lot of stuff. There is a word older in here. That's carrying a ton of heavy lifting in here, as older means like a couple weeks old in this particular case. So if you have like a pretty recent change in OVN, it will not do that anymore. Interestingly enough, this change also solves the time complexity needed for calculating those inequality matches in the first place in OVN, and hopefully solves the problem at all. I was talking more about inequality matches 2 years ago in my talk, but hopefully the problem is finally solved, but we'll see. Still, even if you have like a pair of IPv6 addresses, it's still 228 squared possible masks. So watch out. Users are still a problem. There is some extra functionality in the classifier to support conjunctive matches. We are not going to go into that in this talk, just to save time. But now we need to talk about optimizations. So we now know how the classifier works. Actually, it was pretty simple, as you saw. It's but the second part, the unwildcarding part, is that classifier must unwildcard the mask of a subtable that was examined. So if we look at the subtable, we have to unwildcard all the bits in the mask for this subtable. The issue, of course, is a lot of bits get unwildcarded even if they are not really needed in the mask, which is a problem. It's two optimizations in the classifier attempting to solve it. First, the stage lookup, and second, the prefix tracking. So let's look at the stage lookup. Here you can see I already showed you the struct flow, and actually those can be treated as stages. We can just slice the struct flow in 4 parts, as it is in the classifier optimization. Lines are a little bit blurry inside struct flow. Some of the L3 fields, I believe, were in L4 or something. We had some problems in the past with improper fields being in the wrong stage. Aaron here can attest to that. There's a patch from him fixing some of that stuff. But yeah, it's a big problem, but only for development side. You need to be aware of that. So we have 4 stages: metadata, L2, L3, and L4. Let's split the mask into those 4 segments. Let's hash each segment separately. What's the problem? We have 4 hash maps now. We will first look up the metadata in the hash map. If there is no match, then if there is a match, then we go to L2. We'll hash L2 part. We'll look up in the hash table. If we didn't find, then it means that there are no rules that can match our flow, our packet in this subtable at all. So we can bail early. So we don't have to unwildcard L3 and L4 if our L2 lookup failed. But we still need to unwildcard L2 and metadata as they were used to determine that the lookup failed. So yeah, some pros and cons. We need to do 4 hash table lookups instead of 1, which is, well, just the cost of doing business. We can slightly faster detect subtables that do not match anything, and it's providing us with a significant reduction of the amount of bits that we are unwildcarding per packet. Warning, be extra careful if you are modifying the struct flow. So you need to take into account everything that happens there. One example of how this is relevant for OVN, we had an issue where we were unwildcarding majority we had exact match on IPv6 destination for majority of IPv6 traffic for some reason. And if we just add, this was for MLDV2 traffic, which is supposed to be Ethernet multicast traffic. And the logical flow didn't have a match on Ethernet to be multicast, only on IPv6 to be a specific address. And so if we add this match, then we will bail subtable lookup at the L2 stage, not the L3 stage. And so our IPv6 addresses will never be exact matched in this case, solving the problem. So yeah, recommendation here is to try to add lower matches into the flows if they do not change your logic in any way. I'm not sure if I have enough time. I can very quickly go through the prefix tracking. 2-minute prefix tracking, 1-minute prefix tracking. So people prefer to use prefix matches on certain types of fields like addresses. We can use this to our advantage. For example, if you looked at the original OpenFlow rules, they had 2 matches on /32 and 1 match on /24. We can represent them, if we can look at them as bits and try to create a prefix tree from this. Practically, the prefix tree would look somewhat like this. In the root, we have first 24 bits, then the next 5, next 1, and the final 1. And if we'll try to look up our address .7 in this prefix tree, it will match the root node, and then it will fail on the second node because the bit 29 is 1 in .7. So we can, in this scenario, we would have 2 separate subtables, one for /24 and one for /32. And when examining the second subtable, we can see that the prefix lookup will fail, and we know that bit 29 is actually significant. So we can, and our subtable mask has 32 bits instead of 29, so we know that it cannot match anything for us. So we can only add, we may only unwildcard 30 bits instead of 32 bits. And you can actually see this in the prototrace that I showed you earlier. Our match was /30 for this packet to determine that it doesn't match any of our .1 or .2 addresses. So yeah, there are some more considerations of what's on how to use prefix tracking. The main problem is that they have to be enabled manually. OVN now enables prefix tracking for IPv4 and IPv6 source and destination addresses by default, so it should not be a huge problem. But yeah, the last slide is one example of one major limitation of prefix tracking is it cannot work on non-contiguous masks. So we can see here there was a non-contiguous mask in OVN logical flow. Bits from 112 to 115 were not matched here. So there was a small gap in this IPv6 address, and prefix tracking was not working for this. And this caused all the IPv6 traffic going through OVN routers to have an exact match on IPv6 destination addresses, which are obviously bad. And that's all.
We're kind of out of time, but I guess we can take one question if there is. Yeah, I see one from Han.
Yeah, as you mentioned, for the stage optimization, you can optimize the on-wildcard, but we still had one issue in OVN for the CT new state, we match some CT header, while it generates mega flows even for CT's established state, also match that CT header. So in that case, is there any plan or any feasibility to optimize even further for such cases?
So yeah, it's probably because those fields are in the same stages in the struct flow. So there are options how to avoid that. We can split the struct flow into more stages. It should be possible. Unless there are some dependencies that we need to avoid. So we need to be careful, but it might be possible to split into more stages, and this way avoid unwildcarding some of the other bits. This will come with a performance cost, as instead of 4 hash tables, we'll have like 5 hash tables and so on. But yeah, we can think about that.
Thank you.
Okay, let's thank our speaker again.